Here are two questions to keep in the back of your mind. First, how could something look completely random, different every time you glance at it, and yet be underneath perfectly ordered? And second, if you cooled a handful of atoms down as cold as the universe allows, would they finally lock into some fixed pattern, or would they refuse? Start with something ordinary, a crowd, and one simple rule: everyone must hold exactly one hand. Along a line that is easy, pair up and you are done, around the square. Still easy, but now seat them on triangles, 3 people to a face, and try the same thing. Someone is always left holding no one. The triangle frustrates the rule. Physicists have a lattice built entirely out of that frustration, a web of corner-sharing triangles called the kagome lattice. And here is the instinct almost everyone has. Cool anything down far enough and it freezes. Water makes ice, iron picks a magnetic direction. So surely, at the coldest temperatures, these atoms must settle into some pattern too. Hold on to that thought, because it is exactly the thought this experiment breaks. This is what they actually built, 219 atoms, each held in its own trap of light arranged on a lattice. Look at a single snapshot. There is no pattern. Take another. It is different. Another different again. Every photograph looks like noise, and yet the claim of this paper from Semeghini and colleagues, published in Science in 2021, is that hidden inside that noise is one of the most sought-after states in physics, a quantum spin liquid. And why should anyone care about a random-looking blob of atoms? Because if that hidden order is real, it is a kind almost immune to local disturbances, the holy grail for building a quantum computer that doesn't forget information stored in the shape of the whole, where no local bump can corrupt it. That is the prize that has driven this search for 50 years. And the tool they use deserves a word, because it is the second star of this story, a programmable quantum simulator. Not a computer running code, but a machine where you physically dial in the forces between atoms, press go, and let real quantum mechanics do the work, then photograph the result. 219 atoms, each pinned by its own tweezer of laser light, exactly where you want it. Build the right lattice, set the right interactions, and the atoms themselves become the experiment. So here is the question the whole film is chasing. Is this a genuine, brand new phase of quantum matter? A quantum spin liquid with real topological order? Or is it just an elaborate random mess wearing the costume of one? And how could you ever tell the difference? Let's find out. To see why this state is strange, we need to be clear about what ordinary order looks like. Take a magnet. Every little atomic spin is a tiny arrow. And in a bar magnet, they all point the same way. That agreement is the order, and you can catch it locally. Cover all but a pinhole of the magnet. Look at just a few spins, and they already tell you the whole thing points north. Physicists call that a local order parameter. A crystal is the same story. Peek at a tiny corner, see atoms on a neat grid, and you know the pattern everywhere. Now break it on purpose. Suppose the spins are antiferromagnetic. Each one wants to point opposite to its neighbors. On a line, no problem, up, down, everyone's happy. But put 3 of them on a triangle. The first points up. Its neighbor points down, and the third, it has to disagree with both. And it simply can't, whatever it does. One bond is unhappy, that is frustration, and it is not a flaw you can fix. It is baked into the shape. The kagome lattice takes this to the extreme. Picture 6-pointed stars, tiled edge to edge. A whole plane woven from corner-sharing triangles, named after a Japanese basket pattern. Every single triangle is frustrated, and because they all share corners, the frustration chains together across the entire sheet. There is no clever pattern that makes everyone happy anywhere it is. In a real sense, the most frustrated flat lattice we know, which is exactly why theorists have circled it for decades, as the place a spin liquid might finally show itself. The consequence is enormous. When you can't satisfy every bond, there isn't one best arrangement. There are astronomically many, all equally good, tied for first place. And the count isn't merely large, it grows exponentially with the number of atoms. Double the lattice and you square the number of ground states. For a few hundred atoms, that is more configurations than there are particles in the observable universe. And a system with that many equally good options can't choose. Cool it down, and instead of freezing into one pattern, it keeps fluctuating between them, a liquid, not of atoms, but of the spin arrangement itself. It stays liquid even at absolute zero, where our instincts were everything must freeze. This is the quantum spin liquid dreamed up by Philip Anderson half a century ago, hunted in real crystals ever since, and because you cannot see it locally, never caught red-handed. One subtlety makes this truly quantum, and it is worth pausing on. A merely frustrated classical magnet would just sit stuck in one of its countless arrangements, frozen in decision. What quantum mechanics adds is motion. The system doesn't pick an arrangement. It hovers in a superposition of all of them at once, actively resonating from one to the next, even at absolute zero. That restless zero-point churning is the liquid. Real crystals like Herbert-Smithite are prime suspects. But inside a solid, you can't reach in and read the delicate non-local order. And so, for 50 years, the spin liquid stayed a suspect without a conviction. That refusal to freeze is the first clue and our first takeaway. Billions of arrangements is hard to picture, so let's change the picture. Whenever two neighboring spins pair up into a happy opposite, couple physicists call it a singlet. Draw that pair as a single bond, a little lozenge sitting on the link between them. One bond, one pair, we'll call it a dimer. Now, the rule everyone is paired becomes every site is touched by exactly one dimer. That is called the dimer covering. And it is exactly our handshake rule from the opening, or dominoes laid flat, so they tile the board with none left over. On the kagome lattice, there are, again, exponentially many ways to do it. Each one is a valid covering. Each one looks on its own like a random scatter of bonds. And here is the quantum leap, the heart of the whole idea. The real state is not any one of these coverings. It is all of them at once added together into a single quantum superposition. Every covering present, every covering resonating into the others. Anderson proposed exactly this back in 1973 and gave it a name, the resonating valence bond state. It is the poster child of a quantum spin liquid, and it belongs to a famous family of states called the toric code. The word resonating is doing real work here. Chemists know the feeling in a benzene ring. The double bonds don't sit still. They flicker between two arrangements, and the true molecule is the blend of both lower in energy than either one alone. Anderson's leap was to play that same trick across an entire lattice, with not two but exponentially many arrangements all blending together at once. The blending is what lowers the energy. The blending is the liquid. But wait, if it is just a giant pile of every random arrangement thrown together, isn't that the definition of a mess? How is that ordered? Fair challenge. And it is the crux of everything. It is not a pile. It is one coherent superposition with definite quantum phases relating every piece to every other. The order doesn't live in any single covering. It lives in the relationships between them, in how they resonate. Physicists have a name for this hidden kind of order, topological order. It shows up in three telltale ways. The entanglement stretches across the entire system. Pull two distant atoms, and the whole state feels it. The number of ground states secretly depends on the shape of the surface you put it on. A property will cash in, quite literally at the very edge. And its excitations are fractional particles called anyons. The simplest model with all of this is Kitaev's toric code, and our resonating coverings are remarkably a physical cousin of it. But this raises the obvious problem. If every arrangement is present at once, and each one looks like noise, where could you possibly go to see the order? Take a moment. Where would you even look? Before we hunt for that hidden order, we have to actually build a state. And this is where the experiment is beautiful. Meet the cast. Each atom is a tiny switch with two settings, a calm ground state and a huge puffed up excited state called a Rydberg state. A laser drives the switch, its strength we call omega, the flip. How eager the atom is to be flipped. We tune with a knob called delta, the detuning. And two flipped atoms, both puffed up, push hard on each other. A word on that puffed up state, because it is the engine of everything. Drive the atom with the right laser light, and its outermost electron leaps to an orbit hundreds of times larger than normal. A Rydberg-atom for a fleeting moment 1,000 times more sensitive to its neighbors. Two of these bloated atoms feel each other through a van der Waals force, whose strength collapses as 1 over the distance to the 6th power colossal up close, essentially nothing far away. That razor-sharp fall-off is what gives the blockade a crisp, well-defined radius instead of a fuzzy one. That push is the trick. Two Rydberg atoms repel through a van der Waals force that falls off ferociously with distance. 1 over distance to the 6th power. So there's a radius, the blockade radius, inside which a second atom simply cannot be excited. One excitation claims its own neighborhood. This is the Rydberg blockade. Now watch the correspondence that makes the whole paper work. Put the atoms not on the corners of the kagome lattice, but on its links, one atom sitting on every bond, sitting there. The atoms trace out a second prettier lattice, the ruby lattice, but keep your eye on the kagome underneath, because that is where the dimers live. Every kagome corner is shared by two triangles and touches exactly 4 links. Tune the blockade radius so it reaches all 6 of an atom's nearest neighbors, and no corner can ever sprout 2 dimers at once. An excited atom is a dimer on its link. The blockade, no 2 excitations too close, becomes precisely our lattice rule. At most 1 dimer touching each corner. Push the excitation density up to 1/4, the most the blockade will allow, and every corner ends up with exactly 1 dimer. The blockade doesn't merely permit dimer coverings, it is the rule that manufactures them. This exact idea was predicted on paper by Veresen, Vishwanath, and Polman, just months before it was built. And why 1/4 exactly counted out? Each kagome corner is shared between two triangles and in a perfect covering, needs exactly one dimer touching it. Follow that bookkeeping through the whole lattice, and it pins the fraction of links carrying a dimer at precisely 1 in 4 anymore. And two dimers would have to crowd a single corner, forbidden by the blockade, any fewer, and you leave bare corners, monomers, holes in the covering. 1/4 is the knife edge the entire scheme is engineered to balance on. A blip of laser light is a dimer. The repulsion between blips is the pairing rule. That is our second takeaway. And it is the bridge from a physics lab to a 50-year-old idea about magnets. Let's write down the whole machine in one line, but grow it piece by piece, so nothing arrives from nowhere. There are exactly 3 things going on. The laser flips atoms between ground and Rydberg. That is the first term carrying omega. The detuning offers a reward for being excited. That is the second term carrying delta. And excited neighbors pay an energy penalty. That is the blockade. The third term, flip, reward, penalty. That is the entire Hamiltonian. To reach the spin liquid, they don't just switch the laser on, they sweep. Start with the detuning deeply negative. No atom wants to be excited, so the lattice sits empty. Then, over about 2 microseconds, slide the detuning up through 0 and into positive territory gently, so the system has time to follow along. This is a quasi-adiabatic sweep coax, don't shock. Few real numbers to make it concrete. The atoms sit about 4 microns apart. The drive is a couple of megahertz, and the blockade radius comes out to about 2.5 times the spacing, just wide enough to grab those 6 neighbors and no more. Quasi-adiabatic is the key word. Adiabatic means slow enough that the system stays in step with its lowest available state as you turn the knob. Here it is quasi-slow, but racing a clock because the fragile Rydberg atoms only live for microseconds before they decay. The exact shape of the ramp matters, and they tuned it with care. The detuning follows a gentle cubic curve, lingering where the physics is most delicate and moving briskly where it isn't, and they read the answer only from the heart of the array. The outer couple of rings feel the edge and misbehave. So the real story lives in the bulk, where every atom sees a full symmetric ring of neighbors. And you can watch the lattice fill as the ratio of detuning to drive climbs. The average excitation density rises and then flattens out. Right around 1/4, exactly the filling we wanted. Zoom into a single corner and track the odds. At first it is usually bare, a monomer. Then, past the detuning drive of about 3, the odds swing hard until near 4. About 80% of corners carry exactly 1 dimer. The lattice has quietly assembled an approximate dimer covering, with no one telling it which one. Hold on. You slowly turn the knob and got a different random blob every run. Isn't this just a very expensive random pattern generator? That is exactly the right suspicion, and it is the one we'll spend the rest of the film answering. Keep it sharp. But first, before they reveal a prediction, at 1/4 filling in a perfect covering, how many dimers touch each corner of the lattice? And what would you call a corner that got left out? With no dimer at all. Think it through before we use the answer. One dimer per corner, and the lonely dimer-less corner has a name, a monomer, a defect we'll meet again. Now, to the heart of the problem, the order is invisible to any local look, so we borrow the trick that works for the Tori code. We stop measuring points and start measuring along lines. Give each atom a number, +1 if it is calm, -1 if it is excited, the dimer. Now pick a path that cuts across the bonds of the lattice, and multiply those numbers all along it. That product is our first string operator called Z. Here's the magic of it. Draw the smallest possible loop circling just one corner. A perfect covering always has exactly 1 dimer touching that corner. So the loop crosses exactly 1 excited atom, and the product comes out to -1 every single time. Grow the loop, and the rule generalizes with beautiful simplicity. Enclose 2 neighboring corners. Each contributes its -1. They multiply to +1. Enclose 3, -1 again. Z just counts the corners you fenced in, even gives +1. Odd gives -1. It is pure parity, and it doesn't care which covering you happen to catch. Only that every corner has its 1 dimer. That indifference to the specific arrangement is exactly why a non-local string can see what no local snapshot can. So if the state really is made of dimer coverings, Z on any loop must sign itself by the corners inside. And that is exactly what they see. Pull up the data, a clear non-zero Z, with the right sign holding across a whole window of the sweep and rising to its strongest, right where the density hits 1/4. The state is behaving like a dimer covering. This is the same species of measurement. Kitav's toric code is read out with a loop of operators feeling for a global property. They don't stop at one loop. They measure a whole family of them, a tiny triangle hugging a single corner, and larger loops fencing in more. The smallest gives the cleanest signal peaking right, where the density reaches a quarter. The bigger loops come back weaker. And there's a beautiful subtlety hiding in that weakening. Slip a monomer, a bare corner inside your loop, and it breaks the perfect count. That corner now contributes nothing instead of its dimer. And it flips the loop sign the wrong way. So Z isn't only checking for a covering, it is secretly counting the defects trapped inside it. Hold that thought. 3 beats from now, it becomes our particle detector. One catch, and it will matter later, the signal is never a full one, and it fades as the loops grow. Something is eating away at it, file that away. Quick check, commit to an answer. When we say this state has no local order, what do we actually mean? Is it every snapshot looks identical? B, no small window measurement can reveal the state, or C, the atoms simply aren't interacting. Lock in your choice. It is B, not A. Remember, every snapshot is different, not C. The blockade is a ferociously strong interaction. The order is real, it is simply out of reach of any local probe, which is why we needed a string in the first place. Z told us the state looks like a dimer covering, but a shoebox full of paper coverings would pass that test too. What Z cannot see is the quantum part, whether all those coverings are truly superposed, resonating into one another. For that, we need a second stranger string. Recall that the laser doesn't just read atoms, it flips them. So build an operator called X that flips the atoms all along a loop, turning dimers on where they were off. And off where they were on, do it on a closed loop. And something lovely happens. A valid dimer covering turns into another valid dimer covering. X is the very move that resonates one covering into the next. Take the simplest possible case, a single hexagon of the lattice. There are exactly 2 ways to lay 3 dimers around it, like 2 orientations of a pinwheel. The X loop drawn around that hexagon is precisely the operation that spins one pinwheel into the other. A state that genuinely contains both superposed will register a non-zero X. A state stuck on just one pinwheel gives nothing. So what does it mean to measure a non-zero X? A shoebox of classical coverings would give exactly 0. Flip one and you just get a different sheet of paper. Unrelated to the first, a non-zero X can only happen if the state genuinely contains both coverings. Coherently, at the same time, X is a direct test of the superposition itself. Measuring it takes real cunning, and they're honest about the trick. Your camera only ever sees which atoms are excited, a Z-type readout. It cannot photograph a flip. So first they rotate the whole problem so that the flip becomes something the camera can see. A quick quench, snap the detuning to 0 and crank the laser about 200 times brighter, shrinking the blockade until only the 3 atoms inside the single triangle still feel each other. Why a triangle? Because with a blockade this tight, at most one of its 3 atoms can be excited. So each triangle is a tidy little 4-level system, and you can solve its dynamics by hand. Let it evolve for a precisely chosen time, about 30 nanoseconds. And that collective 3. Atom dance performs exactly the rotation that turns an X string into a plain Z string the camera can read. They even watch it click into place, sweep the quench time and the signal vanishes. Then sharply revives, peaking right at 30 nanoseconds. That revival is the fingerprint that the rotation landed. And the payoff, a clear non-zero X on loop stretching across up to 28 atoms, in experiments lasting only microseconds. That is long-range quantum coherence, spanning a huge chunk of the array. The coverings really are resonating together. And keep the honesty meter running. Each of these strings rides on up to 28 atoms, every one of which could suffer a stray flip or a misread, that any coherent signal survives such a long product. In a system that lives only microseconds, is genuinely striking. The values sit well below a perfect one, as they must. But they are unmistakably, repeatably, above 0. So here is the deep one. A classical stack of coverings gives X equals 0. They measure X bigger than 0 across 28 atoms. What precisely does that prove about the state? Sit with it. Non-zero Z, non-zero X, it is tempting to declare victory right here. So let's do the honest thing and try to break the claim. Here are 2 arguments a skeptic would make, and both of them are wrong in an instructive way. Skeptic's first attempt, the snapshots look random, therefore it is a spin liquid. Number hot, nearly empty lattice, a trivial gas of monomers. Also looks random. Randomness is not the target, it is the disguise the target shares with something boring. Strike 1. Skeptic's second attempt, but the closed loops, Z and X, are non-zero. Surely that is a spin liquid. Also know, and this is a subtle one, a valence bond solid dimers frozen into one fixed repeating pattern can give you a non-zero Z. And the trivial phase can fake a non-zero X. Closed loops alone are necessary, but they are not proof. Strike 2. So lay the 3 candidates out on a single line as you dial the detuning up on the left. Weak detuning, a trivial, nearly empty disordered phase. Mostly bare corners. On the far right, strong detuning, the dimers want to lock into a rigid repeating pattern. A valence bond solid, a crystal of bonds. And somewhere in the middle, if we are lucky, the spin liquid fluid resonating ordered only in the non-local sense. The entire experiment is a hunt for that middle band. So how do you tell the real thing from its 2 imposters, the trivial disordered gas on one side, the frozen valence bond solid on the other? The answer is to compare closed loops with open strings. Here is the intuition. Cut your closed loop in half, giving 2 open strings. If the signal on the whole loop is really just the 2 halves acting independently, if it factorizes into the product of the halves, then there is nothing genuinely non-local going on. The loop was never more than the sum of its parts. That is what happens in the boring phases. In the spin liquid, the loop stubbornly refuses to factorize. The whole is more than its halves. That refusal is a signature of topology. You can turn that into 2 sharp-order parameters, named for the physicists Brickmont, Frötlich, Fredenhagen, and Markov. Essentially a closed loop divided by the square root of its open string. One of them stays lit only for the valence bond solid. The other stays lit only for the trivial phase. And the spin liquid is the single phase in which both of them fall to 0, 2 imposters, 2 alarms. And the target is the silence between them. Before the reveal commit, a finite open X string betrays which imposter, the valence bond solid. B, the trivial disordered phase. C, the spin liquid itself. Choose. It is B, the trivial phase, open X string sprout monomers, which the disordered gas has in abundance, open Z strings, meanwhile betray the solid. And when they run the numbers, the solid's alarm is silent everywhere. And the trivial alarm goes quiet once the detuning to drive ratio climbs past about 3.3. Both alarms off, closed loops on a window from roughly 3.3 to 4.5, where they have caught the onset of a genuine quantum spin liquid. And they nail it down a second. Independent way, if the dimers had quietly frozen into a solid, their positions would betray a pattern, C1 dimer. And you could predict the next. So they measure exactly those density correlations across the array and find them flat, featureless, no hidden repeat anywhere in the liquid window. The valence bond alarm isn't just quiet. There's genuinely no crystal hiding under the floorboards. Let's go back to that fading signal from before. The one being quietly eaten away. It is not noise. It is telling us about the particles that live inside this state. And they are like nothing in ordinary matter. They're called anyons. Take an open X string, a flip along a path that doesn't close. On a covering, it leaves behind 2 defects, one at each end, 2 monomers. In the language of this state, those are electric anyons, E anyons. And an open Z string leaves a different kind, magnetic anyons, M anyons. Subtle phase defects you'd never spot in a single photo of fractional particles, born only in pairs at the ends of strings. Why the odd name anyons? In our 3-dimensional world, every particle is either a boson or a fermion, but these live in a 2-dimensional sheet. And there's something new is allowed. Carry an E anyon in a full loop around an emyon, and the quantum state picks up a minus sign. A memory of the trip that neither a boson nor a fermion has. They can acquire any phase, hence any ons. That braiding memory is precisely the resource you'd store a robust qubit in, and it is why this whole state is worth chasing. The names electric and magnetic aren't just poetry. Think of this state as a tiny universe with its own private electromagnetism, a lattice gauge theory. The E anyons play the role of electric charges, the M anyons of magnetic flux. And the strings we've been drawing are the field lines running between them. It is the very same mathematical skeleton as Kitav's toric code, now built out of Rydberg-atoms sitting on the table in the lab. Now, the fading makes sense. A closed Z loop flips its sign every time it swallows an E anyon. So the more corners a loop encloses, the more likely it hides an odd number of them. And the more the signal washes out, the decay tracks the area of the loop and area alone. That is just what they see for small loops. But look at the larger loops, and the decay bends from an area law toward a perimeter law tracking the edge, not the interior. That bend is a fingerprint. It means the anyons come in tightly bound pairs if both sit inside your loop. Their sign flips cancel, and you never know they were there. They only matter when a pair straddles the boundary. For the X loops, the perimeter law is crisp across loops of up to 32 atoms. The defects are real, they are paired, and the strings can count them. That very crossover from area law to perimeter law, even hands you a length scale for free. It sets in once your loops grow bigger than the typical gap between a bound pair of anyons. So reading where the bend happens tells you how tightly the pairs are held together. And it's a knob you can turn. Prepare the state with a stronger drive and a smoother sweep, and the defect density drops while the string signals climb. The imperfections here aren't a law of nature. They're a dial the experiment can improve. So on the diagram, an open X string makes which anyon, and an open Z string. One creates the electric kind, the other the magnetic, the strings and the particles are two sides of the same coin. We've built a spin liquid and proven its two secrets. It looks like a covering, and the coverings resonate. Now, for the reason anyone chases these states in the first place, watch what a single hole does. Remove just 3 atoms from the middle, opening a small hole in the lattice. Suddenly, the dimer covering split into 2 families, 2 topological sectors. Call them 0 and 1. And here's the crucial part. You cannot slide from one family to the other with any local nudge. The only way across is to flip a giant loop of dimers all the way around the hole, a coordinated 16-atom resonance. The 2 families are protected from each other by the shape of the space itself. This is the promise from earlier finally coming due, the one about the number of ground states depending on the shape of the surface. Punching a hole changes that shape, and topological order answers by splitting into sectors you can only tell apart with a loop that wraps the hole. No local measurement anywhere can distinguish logical 0 from logical 1. And that is exactly what makes information stored in them so stubbornly hard for the environment to corrupt. The enemy would need to reach all the way around the hole to do any damage. 2 protected states, robust against local noise. That is the dream of a qubit. Define the logical 0 and 1 as the spin liquid built from each sector. A Z string running from the hole to the edge reads out which sector you are in. That is the logical Z. A big X loop around the hole flips between them, the logical X. And when they measure the prepared state in the spin liquid window, the logical Z reads 0, while the logical X reads positive, meaning the atoms are sitting in a superposition of both sectors at once. The first fragile step toward a topological qubit. So they built a topological quantum computer, gently. No, this is a first step. And the honesty here matters. They initialize and read the 2-sector superposition. There's no gate here, no braiding of anyons, no error correction yet. And there's a deeper caveat the authors are careful about, so we will be the full system is too large to simulate, exactly. So they check it against the best numerics we have, and those numerics deliver a twist. If you compute the true lowest energy state of this exact lattice, with the full long-range forces included, it is not a spin liquid at all. The long-range tail pushes the ground state straight into a frozen valence bond solid. No liquid inside. So what did they actually make here is a resolution, and it is the subtle heart of the paper. Simulate the sweep itself, the real time-dependent protocol. And it agrees beautifully with the experiment. The sweep is fast enough, over a few microseconds to blow clean past the freezing and capture an equal. Weight superposition of coverings the system could never settle into at rest. So this is a metastable spin liquid, not the ground state, but the state the preparation catches in flight. The paper is careful to call it the onset of a spin liquid phase, and so are we. And if anything, a liquid conjured against the ground state's own wishes is more remarkable, not less. So back to our opening promises, could something look random yet be perfectly ordered? Yes, the order was never in the snapshots, it was in how the coverings resonate. Readable only by strings. And do these atoms, cooled all the way down, lock into a pattern or refuse? They refuse, they stay a quantum liquid. And that refusal is the whole point. Before I sum it up, your turn. Don't just watch, answer. What was it that made a single laser excitation behave like a dimer? What were the 2 strings Z and X each actually testing? What pins the spin liquid between its 2 imposters? And why did one missing hole turn the whole thing into a qubit? Say each one out loud before it appears. They laid atoms on a lattice of triangles, made each blip a bond, and let quantum choice keep the bonds forever unsettled. Every photo looked random, yet 2 long-range strings found a hidden order, and 1 hole turned it into a bit. Remember it as one word, liquid. Liquid, because frustration never lets it freeze. In superposition, every covering at once, quarter-filled blockade. Each blip a dimer, unseeable locally, only the Z string finds it, interfering coverings, the X string proves they resonate. And distinguished and usable pinned between 2 imposters and hauled into a qubit. So where does all this go? The authors are careful. This is a first sighting, not a finished machine, but the horizon is clear. Learn to trap these anyons on purpose and drag them around one another. And their braiding memory could store and process information that no local error can touch. The dream of fault-tolerant quantum computing. And around the very same time, a superconducting chip conjured a cousin of this state by a completely different route. 2 roads now run toward the same strange territory. A 50-year-old question about frustrated magnets has quietly become a new place to build. So I'll leave you with the question the field is now living inside. If a single hole is already a fragile qubit, what could you compute once you learn to braid them? Something to think about.